So next, exercise 51. Unfortunately, those two exercises that we left out in the previous video, I haven't been able to solve them yet. So if and when I do, I will let you know. So today we continue with this one. Suppose that G is a finite group with the property that every non-identity element has prime order. Okay. For example, these dihedral groups are such groups D3 and D5. If the center of G is not trivial, prove that every non-identity element has the same order. Okay. So because the center is not trivial, we can take one non-identity element in the center. So let G be an element in the center such that G is not equal to the identity. Let H be any non-identity element in G. Our aim is to prove that any two non-identity elements in G have the same order. Now, if we can show that the orders of G and H are same, then automatically as you vary H over the group G, the orders of such elements H will also be equal to the order of G, and hence they will also be equal to one another. The orders and Q equal to the order of H are primes. Okay. Since G commutes with H, being a central element, G commutes with every element of the group. In particular, G commutes with H. Since G commutes with H, we have GH to the power PQ equal to G to the power PQ times H to the power PQ. This is true because G commutes with H. Now you can apply one of the rules of exponents and write this as G to the power P whole to the power Q times H to the power Q whole to the power P. These are identity because P is the order of G and Q is the order of H, and that gives you identity. So the PQth power of GH equals the identity. So that means the order of GH will divide PQ. Thus, the order of GH divides PQ. Since P and Q are prime, there are only a few possibilities for this order. Hence, order of GH is either equal to 1 or this is equal to P or this is equal to Q. There is one more possibility also, order of GH is equal to PQ. However, that possibility does not occur because it's given that every non-identity element has prime order. If our GH itself is a non-identity element, its order should be prime. PQ is not prime. And if GH is the identity, then its order is 1. And PQ is not equal to 1, so PQ is not a possibility. So we mentioned that. Note that since every non-identity element has a prime order, we can't have equal to PQ. Okay, now if GH has order 1, then it must be the identity element, because in any group that is the only element whose order is 1. If this is equal to 1, then GH is equal to identity, or G is equal to H inverse. Now we know that in a group, any element which is of finite order is such that its inverse also is of finite order and has the same order as the original element. So P, which is the order of G, is equal to the order of H inverse, and the order of H inverse is the same as the order of H, that is Q. Now assume that the order of GH is P. Okay, then order of GH is P means the pth power of GH will be equal to the identity, but just like this calculation was carried out, because G and H commute with each other, this can be written as G to the power P, H to the power P. Now G to the power P is identity because P is the order of G. So that means we are left with H to the power P. So the pth power of H is identity, so the order of H should divide P. Or we can write here itself, we can write order of H equal to Q divides P. But P and Q are both prime, so if Q divides P, the only possibility is that P must be equal to Q. Similarly, if order of GH is equal to Q, then also P is equal to Q. Thus, if say A and B are any two non-identity elements, then order of A is equal to order of G. We have already shown this. Think of A in place of H, and again, because of that reason, if we take B in place of H, order of G is also equal to order of B. So any two elements have the same order, non-identity elements, and all the orders are prime. So this is the first solution. And then (52) prove that an infinite group must have an infinite number of subgroups. Infinite number of subgroups. Let G be an infinite group. First, we assume that there exists an element A in G of infinite order. Then consider the cyclic subgroups for all positive integers I. Okay, so all of these cyclic subgroups are subgroups of G. Now we claim that they are all distinct. Contrary to this claim, we suppose that two such cyclic subgroups are equal. Contrary to this, we suppose for some positive integers I comma j such that I is strictly less than j. If I and j are distinct, one of them will be less than the other. So without loss of generality, we can assume that I is less than j. Okay. So now from this, we have to arrive at some sort of contradiction. Because I is less than, okay, since this belongs to the first cyclic group, and so this must be an integral power of a to the power j. Or if we want, we can write it in two steps. For some integer m. This implies a to the power mj minus I is equal to identity by one of the rules of exponents. Since a is of infinite order, we must have mj minus I equal to 0, that is mj equal to I. Why? If mj minus I is non-zero, then either it's a positive integer or a negative integer. If mj minus I is a positive integer, then this equation tells us that the order of A is finite, and in fact the order of A is less than or equal to this positive integer, the exponent. But if mj minus I is a negative integer, then from this equation we also get a to the power I minus mj equal to identity, and I minus mj is positive, and again we get the conclusion that A has finite order. So those two things are not true, because the way we have chosen A, it's of infinite order. So the exponent must be equal to 0. But since m is an integer, m is an integer, so m can either be positive, negative or 0. If m is positive, I need to first of all rule out the case that m is equal to 0. M is equal to 0, that will give us from this a to the power I equal to identity, which will again contradict the fact that A is of infinite order. But since m is not equal to 0, as otherwise this will be equal to identity, contradicting the fact is of infinite order. So that means m is a non-zero integer, so the absolute value of m will be a positive integer. Combining this with j greater than I, where do we have here that condition, we get j is positive, this will be greater than I, because m is greater than or equal to 1. So in the least possible case, this left hand side of this inequality will be j. In that case also j is greater than I. And if m is something else, m is something other than 1, then it will be even greater. So this is greater than I, and I is equal to absolute value of I. In fact, I think it will be better if we write here itself, or you continue this. equal to I, but then this part is not needed. So this is contradicted. This is a contradiction and proves that the last supposition is wrong, that is the cyclic subgroups where I is a positive integer in this book. Natural numbers start with 1, so then we can write like this: are all distinct. So that's it, we have obtained an infinite number of distinct subgroups of G. Hence G has an infinite number of distinct subgroups. Okay, so all of this depends on the assumption that G has an element whose order is infinite. Next, assume that every element of G has finite order. Okay. Choose any element A1 belonging to G. Since A1 has finite order, since A1 has finite order, the cyclic subgroup generated by A1 is finite. Since our original group G is infinite, so this cyclic subgroup cannot be the entire G, so there will be something else in G. Since G is infinite, we can choose an element A2 belonging to G minus this cyclic subgroup. Since A2 has finite order, the cyclic subgroup generated by A2 is finite. Also, this is different from the cyclic subgroup generated by A1. Do you see why? That is because this subgroup contains A2, but A2, the element A2 cannot belong to this subgroup. We have chosen it from outside of the subgroup. So these two cannot be equal. Now, the union of these two subgroups is finite, but G is still infinite. So, we can choose one element A3 belonging to this since A3 has finite order, the cyclic subgroup generated by A3 is finite, and just like what we have above, A3 is different from both the other cyclic subgroups. Because A3, the element A3 belongs to neither of them. So the cyclic subgroup generated by A3 can't possibly be equal to either of the other two. Continuing this way, infinitely many subgroups of G. Of course, since we are making arbitrary choices from infinitely many sets to make this, we are getting a sort of sequence of subgroups in the second case also, right? A1, A2, A3. For this sequence to be well defined, you have to invoke the axiom of choice, but that is understood. We usually don't mention such things. Okay, so this is the solution. So in both the cases, we have seen that G must have infinitely many subgroups, distinct subgroups. Then 53. Let P be a prime. If a group has more more than p minus 1 elements of order p, why can't the group be cyclic? Let G be a group having more than p minus 1 elements of order p. Okay, now we have to prove that G cannot be cyclic. Contrary to that, we suppose G is cyclic. Choose an element G belonging to G such that the order of G is P. There are P minus 1 elements, and since P is a prime, P is greater than or equal to 2. So P minus 1 is always positive. So that means G will have at least some element of order P. So small g is one such element. Then this is a subgroup of G of order P, because the generator has order P, so there will be P number of elements in this subgroup. Also, there are P minus 1 elements in this cyclic subgroup of order P. This cyclic subgroup has in total P elements. One of them is the identity element. Order of the identity element is 1. All the other non-identity elements have order P minus 1. This we know. Okay. Now, so we have already obtained P minus 1 elements in this cyclic subgroup, and hence in the original group each having order P, but it's given that the group has more than P minus 1 elements of order P. Now, since G has more than P minus 1 elements of order P, there exists an element H belonging to G minus G, because we have got P minus 1 elements of order P in this cyclic subgroup, but there are more. So if we choose something extra, it will be from outside of this group. So such an element is H, such that this order is also equal to P. Then the cyclic subgroup generated by H has order P, and clearly the cyclic subgroup generated by H is different from the cyclic subgroup generated by G, because this one has the element H, but this one cannot have H because we have chosen H from outside of this. This contradicts the fundamental theorem of cyclic groups, because according to the fundamental theorem, in a cyclic group there will be exactly one subgroup of a given order. If there is any subgroup of that given order, it will be unique. Here, however, we have obtained two subgroups, each one of order P, so that thing is contradicted. So our supposition is wrong, and this has been made possible by our supposition that the original group G is cyclic, which thus must be false. That is, G cannot be cyclic. So that's the solution. Then 54. Suppose that G is a cyclic group and six divides the order of G. How many elements of order 6 does G have? If 8 divides the order of G, how many elements of order 8 does G have? if A is one element of order 8, list the other elements of order 8. So here we can directly use theorem 4.4. In a finite group, if something divides the order of the group, then the number of elements of that thing, that integer, is equal to phi of that integer, where phi is Euler's phi function. If 6 divides then the number of elements of order 6 in G is phi of 6, which will be what? 1, 2, 3, 4, 5, 4. So that means 2, 1 and 5. This is equal to 4, 1, 3, 5 and 7. If A is an element then the others are these powers of A. For this, see corollary 3 to theorem 4.2. That is, here we have to take those exponents that are relatively prime to the order of 8. Relatively prime to the order of A, which is 8. So one of them is 1, which gives us A, and the others are 3, 5 and 7. Then exercise 55. List all the elements of C40 that have order 10. Let X be an element whose order is 40. That have order 8. Order 8 or 10? Order 8, okay. Wait, I think I have taken it down wrongly. Just give me a moment. Now order 10, yes, I took it down wrongly. One can find that these are the elements 4, 3 times 4, 7 times 4, 9 times 4, and for those elements in the cyclic group generated by X which have order 10, correspondingly x to the power 4 and these powers of x to the power 4, 3, 7 and this. Not saying anything else on this, how one gets this thing with whatever result we have come across so far, one can easily see why these should be the elements. Then exercise 56. Reformulate corollary to theorem 4.4 to include the case when the group has infinite order. Just to be sure, here also let me just see one thing before I write anything else. So the corollary is this. The number of elements of order D in a finite group is a multiple of phi of t in a finite group. Now we have to include the case when the group has infinite order. In that case, it's not necessary that the number of elements of order D has to be finite. It may be infinite also. So we write like this: in a group the number of elements of order D in a group is either a multiple of phi of t or is infinite. To see that this infinite case actually occurs, you have to come across a group. You must have come across a group. Now, did we have this example where there are infinitely many elements of a given order? If not, then you think of this. Suppose you consider the we have seen this example before. You consider the set of all polynomials where the coefficients are coming from z2. So each coefficient is either 0 or 1. Now in this there are infinitely many elements of order 2, and in fact and of course with respect to addition of polynomials, this is a group. For example, these monomials all have order 2, and there are infinitely, these are all distinct in this group. So in this group the number of elements of order 2 is infinite. But corollary, have I got it right? I mean, this result doesn't say anything about cyclic group, does it? In a finite group, the number of elements of order t is no, it's just simply finite group, so we are just simply taking infinite group. Fine. Then 57. Determine the orders of the elements of D33. Elements of D33 and how many there are of each. D33 is a dihedral group. It has 66 elements, 33 rotations and 33 reflections. Now I am not going to specifically say which reflections have what order. I will just simply write how many elements of this order are available. So you can see that since the order is 66, okay, and we already know that every reflection has order 2. So there are 33 reflections, so there will be 33 elements of order 2. If you take the reflections out, then you have the rotations, and the rotations form a cyclic subgroup of D33. So in that that is a group of order 33. So from the theorems on cyclic group, that group, cyclic group consisting of all the rotations, that group, in that group each element has order either 1 or 3 or 11 or 33, and we know precisely how many elements of these orders are in the group. Okay, so we will write like this. You write down all the elements of D33. Reflections, of course, you need not write down all the reflections. Each one of them has order 2 that we know in advance. The reflections in D33 are of order 2 each, and there are 33 of them. Among the rotations, there is one of order 1, which is the identity element, rotation through an angle 0 degree. Then phi of 3 equal to 2 of order 3, phi of 11 equal to 10 of order 11 and phi of 33. Phi of 33 is what? 33 times 1 minus 1 by 3 times 1 minus 1 divided by 11. So this is 2 by 3, 10 by 11, so 20. 20 of order 33. So there are actually 20 rotations that generate the entire group of rotations. All of them are generators of order 33. Now exactly which two rotations have order 3, which 10 rotations have order 11, that I leave to you to figure out. You just write the elements and from there you will understand. Then (58) if G is a cyclic group, and 15 divides the order of G. Determine the number of solutions in G. Number of solutions in G of the equation x to the power 15 equal to identity. Then just like that, if 20 solutions in G. And generalize. If X is an element in G such that x to the power 15 is equal to e. Oh, but before this we should have written that g, we should start the solution like this. Such that this is equal to e, then the order of x divides 15. So order of x is equal to 1 or 3 or 5 or 15. Now since G is a finite group, so we can use that result which calculates the number of elements of a given order. G has one element of order 1, phi of 3 equal to two elements of order 2, phi of 5 equal to 4 elements of order 5 and phi of 15, that is 15 times 1 minus 1 over 3 times 1 minus 1 over 5. So 2 times 4, 8. Elements of order 15. And clearly such elements will satisfy this equation. Hence, the total number of solutions is 1 plus 2 plus 4 plus 8 equal to 50. Next, assume that 20 divides the order of G. Then the number of solutions of or in G of this equation x to the power 20 equal to E is now from our experience in this case, we can directly write phi of 1 plus phi of 2. 3 does not divide 20, 4 does, 5 divides 20, 6, 7, let me just calculate the number of, what am I calculating? Hold on. 120, 2, 10, 4, 5. Yeah, these are the only divisors. One plus 1 plus 2 plus 4. What about 10? Phi of 10. 10 is 10 times 1 minus 1 by 2 times 1 minus 1 by 5. So this is also 4. What about 20? 20 also has these two prime factors, 2 and 5. So it will be 8. Is it correct? Yes. Generalize. If G is a cyclic group and is a finite cyclic group actually, and N is a positive integer that divides the order of G, then the number of solutions in G of the equation x to the power n equal to E is n. To prove this general one, it seems that we have to prove that if one adds the 5 values of all the positive divisors of a given positive integer, then one gets the integer back. Actually, this is true. This is a property of the phi function which we will prove in number theory. So this is 58, then 59, if G is an abelian group, and contains cyclic groups. Cyclic subgroups. Of orders 4 and 5 what other sizes of cyclic groups must G contain? And generalize. Okay. Since G has cyclic subgroups of order 4 and 5, where 4 and 5 are relatively prime, so that means you can consider, you see, cyclic subgroups are there in G of order 4 and 5. So that means you will find their generators, they will have some generators, each one of them. Those generators will be elements of order 4 and 5. And 4 and 5 are relatively prime. So there will be an element in the group whose order is the LCM of 4 and 5, that is 20. And that element will generate a cyclic subgroup of order 20. In that cyclic subgroup, you will have its own cyclic subgroups of orders that are divisors of 20. That is all these things. One, 2, 4, 5, 10 and 20, out of which 4 and 5 are already given. So we just simply write like this. G must contain cyclic groups of orders 1, 2, 10 and 20 besides that 4 and 5. And the generalization is this: in general, if an abelian group contains cyclic subgroups of orders m and n, where m and n are relatively prime, then it contains a subgroup of order, or it contains subgroups of order D for each positive divisor D of Mn. Mn is the LCM of M and N if M and N are relatively prime. And the justification of all these things is for that you see exercise 41 above. And finally, there is a similar one, exercise 60. If G is an abelian group, and contains cyclic subgroups of orders 4 and 6. What other sizes of cyclic groups must G contain? Here also the solution is similar. The only difference is that now 4 and 6 are not relatively prime. That is not a problem. Same, LCM of 4 and 6 is 12. So G will have a cyclic group of order 12 because you will find an element of order 12 from the elements of orders 4 and 6. That is taken care of by this exercise 41. So in that cyclic group of order 12, you have the positive divisors 1, 12, 2, 6, 3, 4. For each such divisor, there will be a cyclic group of order equal to that divisor, among which we already have 4 and 6. So the other possible sizes are 1, 2, 3 and 12. And generalization is just like that. In general, in an abelian group, that contains cyclic subgroups of order m and n, and now not necessarily that m and n are relatively prime. Okay, so we drop that assumption. Subgroups of order m and n, then it contains a subgroup of order d for each positive divisor d of the LCM of m and n. That's what we have done here. Here 12 is not 4 times 6 but LCM of 4 and 6, and this also is justified by exercise 41. So you can just simply write similarly the solution. I am not writing it. So with that I end the video here. If you want to say something, you are welcome to write in the comment section below. So until the next okay, what do we have tomorrow? Group theory. So that will be all. So this is me, Lucifer, from a mathematical group. Have a nice night and stay safe.